Hello again, Physics 20s. In today's lesson, we are going to continue our discussion of simple harmonic motion, although this time we're going to look at the simple harmonic motion of a mass spring system. However, before jumping into the lesson, I did just want to quickly review the two conditions that are necessary for an object to exhibit simple harmonic motion. The first one is for an object to exhibit simple harmonic motion, there needs to be a repetitive motion, and there needs to be a repetitive motion where you have a constant frequency or period. This isn't totally realistic. Again, going back to the previous lesson for the pendulum Earth system, so as that pendulum swings back and forth, due to the air resistance over time, the pendulum would eventually come to rest, in which case there's no way that the period or the frequency can be constant. However, if you ignore air resistance, and I believe if you release the pendulum at small angles, it does move back and forth at a constant frequency or period for a relatively long period of time. The second condition is that for an object to undergo simple harmonic motion, it needs to be subjected to a restoring force. What does this restoring force do? So restoring force is always trying to get your object to go towards the equilibrium position. In fact, the direction of this restoring force would always be pointing towards equilibrium. Learning outcome for today is to explain quantitatively the relationships among displacement, acceleration, velocity, and time for simple harmonic motion as illustrated by a frictionless horizontal mass spring system. We're also going to look at a vertical mass spring system, but most of the emphasis in the lesson will be dealing with horizontal motion. Well, let's start off by talking about the restoring force for a spring. When you take a mass that's attached to a spring and you either stretch it or you compress it a certain distance from equilibrium, and once again, the equilibrium is, you can envision it as being the position where the object would eventually come to rest. A restoring spring force, Fs, causes the object to accelerate towards equilibrium. Let's look at a few different positions that the mass and the mass spring system can be. Position 1, equilibrium. So once again, your equilibrium position would be the position where the object would either start from rest or eventually come to rest. Although as the object in the system is moving, it will pass through the equilibrium position like many times. Your equilibrium position, and if we define the position vector x would be 0 when the spring here is not stretched nor is it compressed. Let's say now that I take this mass and I pull it over towards the right. If I do that, now the spring is stretched. So I've displaced the object over towards the right. And now, when you do this, the spring always wants to go back to its unstretched position. Therefore, you'd have this restoring spring force that is always pointing towards equilibrium. If you want to think of what this restoring spring force is like, it's kind of like an applied force. However, when we draw free body diagrams, we're actually going to write down the variable Fs for the spring force. At the start of the dynamics unit, we introduced 4 big forces: force of gravity, normal force, applied force, and the friction force. And this would be another force to add to it. So the restoring spring force behaves differently in comparison to any of those 4 forces. So even though you can think of it as being an applied force the spring exerts on the mass, the way the restoring spring force behaves is a little bit differently. So it's going to get its own variable. And we're going to go through an equation we can use to calculate it in a moment. Okay, so we pull this thing to the right. The restoring spring force is pointing towards equilibrium. It's always trying to get you to go back towards the unstretched position. Then we let go, and then this mass would then accelerate all the way over towards the left. And then it would reach a point where the spring is fully compressed as much as it possibly can be. So at this position, in comparison to your equilibrium position, you're now over towards the left, and then your restoring spring force is always pointing towards the equilibrium position. Therefore, now it is pointing towards the right. So I can see how I have a restoring force that's always trying to get me to go towards the equilibrium position. Just like I had with the pendulum earth system. The pendulum earth system, my restoring force was the parallel component of the object's weight. And by parallel, we mean parallel to the direction that the object is moving at that instant. Hooke's law is going to allow me to calculate this restoring spring force. It tells me that the restoring spring force, Fs, is directly proportional to two things. One, the spring stiffness K, and two, the position of the object from my equilibrium position. I'm going to provide two equations. One is going to deal with magnitude and one will deal with direction. Let's worry about the magnitude first. So this equation, which tells me the magnitude of the restoring spring force, and if I wanted to abbreviate it, I could just write it down as Fs, is equal to K times X. That's the magnitude. Or if we write it, the restoring spring force down as a vector, this is the equation you're going to see on the formula sheet, we'd have Fs is equal to negative K times X. And the question really is, why is this negative sign in the equation? We'll look at that in just a moment. But first of all, let's identify the variables. First one, K is something called the spring constant. The spring constant is just a measure of how stiff the spring is. So some springs, it's very, very difficult to pull and stretch them in comparison to other ones. The more difficult it would be to take that spring and pull it from its equilibrium position, the greater the spring stiffness would be. It's usually measured in units of newtons per meter, and here's how I'd interpret the units. So for example, if I had a spring stiffness that was K is equal to 50 newtons per meter, the way I would think about this to try to visualize what the force kind of looks like or how it's behaving would be if you took the spring and stretched it by 1 meter, then at that position your object would experience a restoring spring force of 50 newtons. If you had a larger spring stiffness or constant, 100 newtons per meter, then it means if you took that same spring and you stretched it by, again, a 1 meter distance, this time around the object would be subjected to a much larger force, 100 newtons. Therefore, the larger the spring stiffness or constant, the more difficult it is to stretch the spring, and the greater the force is going to be to try to get it to go back towards the equilibrium position. And we can see this because of the direct relationship between Fs and K. If K gets bigger, then Fs gets bigger. X, by the way, just represents the position of the object from the equilibrium position. In terms of why this negative is here, this negative is here because it's a reminder that your two vectors, which are the restoring spring force and the position of your object, they are always opposite in direction. So let's look at this. For example, if I take the object from equilibrium and I pull it towards the right, well, let's say that right is positive, therefore the position of my object would then be positive. Your restoring spring force would then be pointing towards equilibrium, and equilibrium would then be towards the left. Therefore, the direction of that force would be negative. If you look at the actual sign convention in the equation, so let's say we plugged in all the different signs. So let's plug in, we have negative. K is always a positive number. And if we plugged in an X value that is positive, what that would do is a negative times a positive would give me a negative value. Therefore, if my displacement is towards the right, this equation ensures that my direction for my restoring force is going to be opposite, towards the left. What happens if we let go of this thing and now it was over here? Well, if it's over here now, then the position of your object, x, would now be towards the left, which is negative, and your restoring spring force would now be towards the right. So if we plug the signs in again, so this would be Fs is positive, so we'd have negative times k, which is always a positive. This time, in our compressed position, the object's located towards the left, therefore it would be negative, and you'd have a negative times a negative, which would give you a positive. So no matter where you are in the motion of the mass and the mass spring system, the restoring force and x will always be opposite in direction, except when you're at equilibrium. When you're at equilibrium, x would be 0, and if x is 0, so is your restoring force. It turns out, though, that when we write our equations of motion, we like to deal with the direction from a free body diagram and then just treat everything else as magnitude. Therefore, we're going to use this equation, the one with magnitude, more than this one. In fact, the only thing that we'll even remotely refer to this one as is when we draw the free body diagram, try to identify what direction Fs is. But otherwise, we're not going to write down the Fs is negative kx, just write down the magnitude of the equation. Let's also look at the velocity and the acceleration of the object in a little bit more detail. Okay, first things first, looking at, so what I have here is I have a graph of acceleration as a function of the position of your object. I know it says displacement here, but let's just change it to position. And the important thing to note immediately is if you look at the graph, the acceleration from point A to B to C is non-uniform. It's constantly changing. This is very unusual for us in Physics 20 because for the most part in Physics 20, when we talk about accelerated motion, the acceleration is uniform. For example, if you had an acceleration time graph of a free-falling object, free-falling object has a constant acceleration of negative 9.81. Therefore, your graph would just look like a horizontal line here. Well, for the motion of a spring, our acceleration is non-uniform. This is going to add some complications in later because when we start to deal with this mathematically, we are not going to be allowed to use any of those kinematics equations that have d, vi, a, t, and vf in it because those equations are restricted to uniform acceleration. Now, I want to provide a bit of a justification as to why do we get the actual shape of this graph. Well, let's say we looked at a free body diagram of the mass. Let's just look at it at point A. So we have an FBD. We'll say point A or position A. Only going to draw the horizontal forces here. We'll learn about the vertical forces in a later problem. For now, just the horizontal one. So in this position, you're in the compressed position, and you have one force acting horizontally, and that horizontal force would always be towards equilibrium. So you'd have Fs is towards the equilibrium position. If you drew an MAD, you'd have your mass, and you'd have your acceleration. So in this case, the restoring spring force is going to be the net force. And let's write down the equation of motion to show this. So if we say right is positive, and I find the sum of my forces in the x direction, and that's equal to mass times acceleration in the x direction, this would turn my equation into what's the net force in the x direction? It's the restoring spring force. You'd have Fs, it's positive because it points right, multiplied by m times positive a. Now, we have an equation for the restoring spring force. According to Hooke's law, the magnitude of the restoring spring force is just the spring stiffness or constant times the magnitude of my position from equilibrium. And that would be equal to m times a. If I manipulate this equation for my acceleration, I would then have A is equal to K times X over M. For a particular mass spring system, your K would be a constant, and so would M. Therefore, we can just look at a direct relationship between A and X. And a direct relationship means that it's going to be linear. Now, you might be wondering, well, why isn't it just going to be a graph that goes up and towards the right? Well, now we have to consider the direction. So if we go to point A here, at point A, your restoring force would be towards the right. And if your restoring force is towards the right, your acceleration is also towards the right. If your acceleration is towards the right, then your acceleration is going to be positive. So we have to start off at a positive acceleration up here. At the equilibrium position, well, according to Hooke's law, if Fs is k times x, actually, we don't need to worry about that. If we look at, I already derived the equation. If we look at this equation, so we have A is equal to kx over m. If your x is 0, which is the equilibrium position, you don't have any acceleration. So therefore, I would have nothing here. And then if we're at the fully stretched position, well, at the fully stretched position, your restoring force would be towards the left. And so would your acceleration, because your acceleration is in the same direction as your net force. Because acceleration is towards the left, then this would just be negative. Therefore, you need to have negative acceleration here. So I do get this direct variation, although a direct variation where you have a negative slope just to properly account for the direction of the acceleration of the object in the system we see here. How about velocity? Well, before we do this, remember that back in the 1D kinematics unit, that if we had an acceleration time graph and we went back to a velocity time graph, oops. Okay, sorry about that. Velocity time graph. There was a connection we looked at between the degree of the equation. If we go backwards a graph, so we go from acceleration time to velocity time to position time, what we do is as we go backwards, we add 1 to the degree of the equation. So that kind of helps me in predicting what shape is the graph going to be if you work backwards. In this case here, this is a straight line. A straight line has a degree of 1 for an equation. Therefore, if I go backwards by 1, I'm going to expect my velocity time graph to have a degree that is 2. A degree that is 2 is technically like a parabolic shape, but we'll just say it's curved if you go backwards. Okay, so let's look what the graph would be here. And let's try to make sense of the actual graph. Okay, so let's say I started at point A by just pushing this spring towards the left and I released it from rest. If you release it from rest at position A, then it's not moving at position A, therefore your velocity is 0. Then it goes through past equilibrium all the way over to point C. Now at point C, what happens is there's a direction change. So it's moving towards the right, and then it changes moving towards the left. It's kind of like if you take an object and you just like toss it straight up in the air. At the very top of its arc, there's that one brief moment where the direction change occurs that you're not moving. And same thing here. When you get to the fully stretched position, then you would also not be moving at position C. And then when you go back towards the compressed position, once again, there's a direction change, so you're back down to 0. The other one is, okay, so why is the velocity a maximum at the equilibrium position? Okay, so here's how we think about this. So let's say we're going from point A to point B. When I go from point A to point B, your velocity is towards the right, and your acceleration is towards the right. If these two vectors point in the same direction, this tells me that my object is going to speed up. Now, the instant you pass equilibrium, what would happen? Well, you'd have your velocity still towards the right, except now they're restoring spring force, and therefore the acceleration is going to reverse direction. So now it would be towards the left. So the instant you pass equilibrium, the direction of acceleration reverses, and if these two vectors are in opposition to each other, then that's going to cause the object to slow down. Therefore, the fastest you can be moving is at equilibrium, because when you approached equilibrium, you had acceleration and velocity pointing in the same direction. The instant you pass equilibrium, they're now opposing vectors and you would slow down. And the only other thing that remains is if you know these 3 points, that if you have no velocity at your fully compressed or stretched position and max velocity at the equilibrium position, how do you know it's curved? Well, we already talked about that. When you go from an acceleration time graph to a velocity time graph, or in this case, we're using a acceleration as a function of position graph. Same thing. We go back by 1 in terms of the equation. That makes my degree go up by 1. Therefore, you have a degree 2 equation, which gives me the curve shape that you see. Period. To calculate the period of a spring, and we refer to it as the period of oscillation, and the period of a mass, m, that's attached to the end of the spring, we get an equation that's identical in format to the one that we had for the period of a pendulum bob in a pendulum earth system. So this is also on the formula sheet. We have the period is equal to 2 pi multiplied by the square root of m divided by k. And as we know, k is the spring stiffness. Therefore, the period does not, well, I should say therefore, but one thing to make note of is that the period does not depend on the amplitude of oscillation or the gravitational field strength at the location of the mass spring system. Okay, let's go back and let's try to explain what's going on with all these variables here by looking at an actual illustration. Okay, I'm just going to get rid of all this ink on the page here. Okay, so we have the period is equal to 2 pi multiplied by the square root of m over k. So first things first, the period would be the time it takes for, if we start at position A, the spring goes all the way over to position C, it needs to return back to where it started. So one period of oscillation would be the time it takes for the mass to start at position A, go to the other side, and then come all the way back. That would be my period. Now, in terms of the actual variables, so let's look at why there's a dependency on m and k. Let's look at the k one first. If you look at the variation between period and k, it'd be period is inversely proportional to the square root of k. So there's an inverse variation. So what that means is that if your spring stiffness is bigger, then the period is going to be smaller. I don't think that's surprising, because if k is a lot bigger, then so is my restoring force. Therefore, it's going to make me just oscillate a lot faster. For the other ones, look at the equation we derived for the acceleration of the object in this system. So that equation we had was A is equal to kx divided by the mass. I wanted to talk about why doesn't the amplitude matter again. So for example, if we took this and we placed the object here and then let go, and it just oscillated between these two positions. Again, the amplitude is your maximum position from equilibrium. Why doesn't the amplitude matter? Well, think about this. If your amplitude is bigger, then that's going to mean your x is bigger. If your x is bigger, since there's a direct relationship between a and x, that means your acceleration is going to be bigger. So if you have the larger amplitude, once again, just like with the pendulum, you have that greater distance you need to cross. You have to go all the way over here, back to there, as opposed to covering this smaller distance if my amplitude was smaller. So how can I cover this extra distance in the same amount of time? Well, if your amplitude's bigger, so is your acceleration. If you have a larger acceleration, you have a larger change in velocity, which enables me to cover that larger distance in the same amount of time. So again, you can once again draw a comparison between the mass spring system and also between the Earth pendulum system. Okay, so again, we got that equation. T is equal to 2 pi squared m over k. And let's do a couple of examples now. Okay, we're dealing with a vertical spring. So it says, when placed at the bottom of a vertical spring, a 2.45 kilogram mass causes the spring to stretch 12.4 centimeters before coming to rest. Now I want to calculate two things, the spring constant K, and I also want to calculate the period of oscillation. Let's look at two different positions of my object, or two different states. So first of all, let's say we have our spring, but there's no mass attached to it. So if I draw this, let's draw like a ceiling. And here's my spring. And we'll say right now, we're going to use this to identify the position where the spring is initially unstretched. And then we're going to attach a mass to it. When you attach a mass to this vertical spring, it's going to make it stretch. So then perhaps a spring then looks like this. We got a mass attached to the end of it. What it tells me in the problem is that when you add this mass to the bottom, it causes the spring to stretch down by 12.4 centimeters. So we're going to turn that into meters. We'll turn it into 0.124 meters. Okay, so I put this mass at the end. It would start to oscillate and undergo simple harmonic motion, but it tells me eventually it does come to rest. Okay, so we want to figure out the spring constant. Now, we can't do that from Hooke's law right now because we don't know what the restoring spring force is. Therefore, our default when we don't really know what to do should always be to go to a free body diagram, especially when we're talking about forces. So let's draw a free body diagram of my mass. So we're going to look at it at this position when it's come to rest at this position. So at that position, you would have the force of gravity that is straight down. And if I'm at rest, the forces are balanced. Therefore, the restoring spring force, and again, your restoring spring force is always trying to get you back towards the unstretched position. So your restoring spring force here would be up and towards just up to straight up. So Fs is straight up. Mass acceleration diagram. Here's my mass. And there is no acceleration. It's equal to 0 because we are at rest. So let's write down our equation of motion. So if we look at the sum of the forces in the vertical direction, this would just be equal to 0, and it's equal to 0 because the forces are balanced. Expanding the equation of motion would turn into, well, Fs is up, therefore it's positive. Fg is down, it's negative. So you have Fs minus Fg is equal to 0. And let's expand the equation to motion now. According to Hooke's law, the magnitude of the restoring spring force is just K times X. And Fg is m times g. And now we can manipulate this equation for K. So if I add mg to both sides of the equation and divide by x, I would get K is equal to mg over x. And now we can plug the numbers in to get the spring constant. So the mass is 2.45 kilograms. Multiplied by the magnitude of the gravitational acceleration, 9.81 meters per second squared. And then divide this by x. And x is converted and it must be in meters. Reason being the numerator, kilograms times meters per second squared, that's equal to a Newton, and typically want to write the spring constant down in units of newtons per meter. Okay, 3 significant digits. This would give me a spring stiffness or constant of 194 newtons per meter. Again, the way to interpret that would be if you took the spring and stretched it by exactly 1 meter, there would be a 194 Newton force acting on the mass at that position. Okay, B, let's calculate the period of oscillation. Well, we can just use our equation now to do that. So we have T is equal to 2 pi times the square root of m over k. And then let's plug some numbers in here. So this would be 2 pi multiplied by m. And then we have 194. Oops, not 194. We're going to plug in the m value here. Okay. 2 pi times m, which is 2.45 kilograms, divided by the spring constant. The spring constant we got from part A, 194 newtons per meter. And this would be T is equal to 0.706 meters. By the way, if you're wondering, like, why is there's a direct square root relationship between the period and the mass, which means that if m goes up, then the period is also going to go up. I think the way I would justify this one is qualitatively. If something has a larger mass, it has more inertia. If it has more inertia, it's more difficult to change whatever it's doing. So in this case, whatever direction it's moving. So with a larger mass and larger inertia, it's more difficult to change the direction of the mass. And consequently, that would result in you having a larger period. Example 2. Okay, so now we're on a horizontal surface and we have a 0.724 kilogram mass with a spring stiffness attached to a spring, stiffness of 8.21 newtons per meter. It's on a frictionless surface. We pull it towards the left by 0.5 meters and release it. We want to figure out what the magnitude of the acceleration is when it is 0.362 meters away from equilibrium. Okay, let's draw a few pictures just so we understand what's going on here. So I'm going to draw my wall over here. And then I'll draw my mass located at this position. And let's just represent the equilibrium position as going straight through the center of the mass. So this would be equilibrium. And then we're going to take this and we're going to pull it towards the left. So I'll draw this again. Let's maybe put it right here. So this would now be 0.500 meters. So we start at equilibrium. move it over to the left, let go. And then we want the acceleration at an in-between state. So the in-between state would be something like this. So again, I'll draw my wall here. And then my spring looks kind of wonky, but that's okay. Okay, and this distance would then be 0.362 meters. Okay, so we want to get acceleration. The only way we can do that is from a free body diagram, a mass acceleration diagram. So we'll do this. We'll go in FBD. And this is going to be at the position where we're 0.362 meters from equilibrium. So I'll say 0.362 meters, not 4, from EQ. And we'll also draw a mass acceleration diagram. Okay, we'll draw a full free body diagram here, although we don't really need to because we're only looking at the horizontal forces. So we're on a horizontal surface, therefore we'd have the object's weight that's straight down, that's Fg. And then we'd have the normal force from the surface pushing back on the mass, so it'd be straight up. And then if we're towards the left of equilibrium, again, the restoring force always points towards the equilibrium, so you'd have Fs points towards the right. Draw the MAD. Here's your mass. And if you have one net unbalanced force, then you got to have your acceleration in the exact same direction. So your acceleration is also towards equilibrium. Let's write down the equation of motion. So look at the sum of the forces in the x direction. And this time around, they're unbalanced. Okay, so sigma fx would expand to fs. We actually derived this equation earlier on in the notes. So the fs is equal to m times positive a. Fs, according to Hooke's law, the magnitude of that restoring spring force is k times x, and that would be equal to m times a. And we want to solve for the acceleration, which is equal to kx divided by m. Now all we have to do is just plug the numbers into the equation. So your spring constant is 8.21 newtons per meter multiplied by x. The magnitude of that position from equilibrium is 0.362 meters. And then divide this all by the mass of that object, which is 0.724 kilograms. And then that's going to give me an acceleration magnitude that is 4.11 meters per second squared. So once again, we're continuing to use this same problem-solving approach where we draw FBDs, MADs, and then write equations of motion that mathematically model the situation, and can use that even now to solve problems dealing with springs, understanding that we have a new force now, the restoring spring force, which the magnitude can be calculated by k times x. All right, so that's it for this lesson, and you can complete the assignment called Simple Harmonic Motion of Springs. And then I believe in the next lesson, we're going to shift gears and we're going to start to talk about work. And I will talk to you then.